This is a quick video about how JITX works. So JITX is a way to design circuit boards with code. So here I have a design, just a single resistor. If I change this resistance to 220 and rerun it, I'll get a new schematic and I'll get a new board, now with a new resistor. Now to add more to this design, I could keep editing code, or what we could actually do is just throw it off to AI. So it'll say add another resistor and connect them. So here it's going to take that request and go write some code. And it's going to do all sorts of fancy A stuff to generate the code itself. But once I have that code, it's here, it's locked in, it's precise, and I can understand it. So here it's added a 330 ohm resistor, which is fine because I didn't specify anything else. And if I run this code, then we should get our new resistor showing up in the board. Here's a schematic. Notice that you can move it around and customize it. And we've got our other resistor in the board as well. So obviously we can add more than resistors from code. So I could ask what connectors are available. And here it's going to look at my local code libraries. And these libraries, just like this code, were created by an AI, where you can take existing CAD models or existing data sheets and load them into the AI, and it'll do all of the parsing and then create code-based models of the parts. So here it's summarizing in the starting library, I have a USB-C connector, an Ethernet jack, and some terminal blocks. Now let's do something a bit more complex. So we're going to implement designs from requirements. So we can write out plain language requirements like either we got an industrial I/O board, we're going to have a microcontroller with USB 2, isolated digital inputs, RS-485, and 24-volt power. So now I can say implement the requirements. And what it's going to do is use its code searching tools to go find functions that support these requirements, the microcontroller, the transceivers, the isolated I/O, and then implement the design using code. Okay, so now that it's discovered the components and inspected them, it's going to go ahead and start writing design code. Okay, with the draft code in place, it's going to try running the design and seeing if it finds any errors. Okay, and now that the design is in place, it's refactoring the code to make everything nice and clean. All right, so here we have the final design, and we can go ahead and read through the code. We have 24-volt input, 5-volt buck regulation which drives this parametric power regulator. A linear regulator, which was the LT1763. And then here it's going to be implementing the rest of the design. So it separated stuff out into functions, which is fine. Just create power, create nets. It's going to create the microcontroller, add the isolator circuits, RS-485, and then finally connect everything together. So we can see on the board here. So if we look at the design, we can see that we have our board and schematic. I'm going to show you a couple more things. So one, the microcontroller has been modeled, not just with its connectivity, but also for pin assignment optimization. So I can show that on this, say this UART-based RS-485 transceiver. If I route one of these pins, which is the RX pin, so only the compatible pins on the microcontroller are highlighted. And now that that's constrained, then we can route TX to the same interface. And you see that if If we write a GPIO, for example, then many more options exist for the I/O. So it also sets up the high-speed differential constraints for the USB as well. So here I can run this differential pair, and it's going to come in with the skew constraints and impedance and loss constraints for the USB 2 interface.